Hello, my name is Bob Card and the AMG Marketing Manager for the Americas. Today's webinar is going to be Unlocking the Power of Image Sensor Power Tree. For an agenda, we'll first start with a tutorial. I'll touch on buck and LDO fundamentals. Then I'll go into talk about when to choose a buck over an LDO. This includes power dissipation calculations, theta JA discussion, die temp or junction temperature, and also enclosure and module thermal effects. Then we'll pivot over to the Hyperlux image sensor power rail sensitivities, talk about power supply rejection ratio, V out, and then the LDO transient response. Specifically, we'll do a comp analysis with our new Treo LDO that ends in 165 versus the competition. And Treo is our new fab process within onsemi. That's a 65 nanometer fab process from 1 to 90 volts. And is also 300 millimeter at East Fishkill, New York. And then we'll look at the NCV 92310 PMIC or power management IC. And then we'll pivot to the Hyperlux power tree, which has 11 one-pagers that summarizes the bill of materials, the web pricing, the block diagram, assuming worst case image sensor configuration with respect to power consumption and also 60 degrees ambient temperature. And then we'll wrap it up with some block diagrams for local and remote image sensor processing power tree, featuring our PMIC as well. And I do want to highlight that this tutorial really is a pretty good, that you can apply this tutorial to any load really. So it doesn't have to be image sensors. I just happen to use that as a vehicle for this. Okay, so for buck converter basics, you've got your controller up here in the top left. It's controlling an integrated high side or Q1 and low side or Q2 MOSFETs. And then at the drain of the low side or the source of the high side, it connects to an external inductor, which then goes to a load. And the theoretical V out equals V in times the duty cycle. And so if you have a V in at 12 volts and your duty cycle is 50%, you're going to get a 6 volt V out. If your V in is 12 volts with a 75% duty, you're at 9 volts out. And with 12 volts in 25% duty, you're at 3 volts out. And one of the main things is you never want to churn Q1 and Q2 on at the same time, because that'll be a short to your input voltage. So you always exercise shoot through current prevention or cross conduction prevention with inserting some dead time. So you never turn on 1 and 2 at the same time. There is always going to be some V out ripple with this device. You've basically got an internal oscillator in this controller. Could be hundreds of like 500, 600, 700 kilohertz, or megahertz, 2 megahertz, 3 megahertz, 4, 5, 6 megahertz. And that's going to drive a little bit of ripple on the output. You can decrease the ripple by increasing the C out or increasing the switching frequency. This oscillator can cause a little bit of EMI, so you need to be mindful of that. And then also the shoot through current, as I mentioned below. So the two major steps or states for the synchronous buck, I forgot to mention, a synchronous buck is called a synchronous buck because Q1 is always synchronized to Q2 and vice versa. And so during the on time, Q1 is on, Q2 is off. That's when you're storing energy in the inductor. And then during the off state, which is when Q1 is off and Q2 is on, that's when you're delivering energy that's stored in the inductor. You're delivering that energy into the load. And so your synchronous buck converters typically run in continuous mode with medium to high loads. And that's where the inductor current, as your PWM or duty cycle, your states, that's where your inductor current never goes to zero. But sometimes with the lighter loads, that inductor current does go to zero. And if you have those lighter loads, for continuous mode, you typically use pulse width modulation, where you vary the duty cycle at a given frequency. Now, when you get to these discontinuous mode, during this, zero inductor current, you don't have any conduction losses because you don't have any current flowing. So then your losses are dominated by switching losses. So you can go to what's called PFM during discontinuous mode, where the inductor current goes to zero, where in PFM, you vary the frequency at a given duty cycle. That helps to minimize those losses. Speaking of losses, synchronous buck converter losses are typically broken up into two major categories: conduction losses, switching losses. I've also included static losses, which is, I would argue, a minor minor amounts, mostly dominated by conduction losses and switching losses. Your conduction losses are governed by I squared. So that's the RDS on times the current squared going through the switch whenever they're on. So that attributes to a lot of losses. And of course, if you want to reduce your losses, you reduce your RDS on of your MOSFETs. In contrast, you have switching losses, which are the losses incurred going from high to low, turning on and off these switches. So if you want to solve for I in for this particular buck scenario, you've got 5 volts coming in. You've got a 350 milliamp load running at 1.8 volts. This buck is going to step down the input 5 volts to the 1.8 volts output. How do you solve for I in? First, you need to look on the data sheet and find out what that efficiency is for this V in and V out and I out. In this particular case, it's 90%. And then there's 3 steps for solving for I in. First is the power out, which is the V out times the I out, essentially the load. Power in equals power out divided by the efficiency, which we got from the data sheet. And I in equals power in in watts divided by the V in voltage. And so for this example, with 1.8 volts at 350 milliamps, the power out is 0.63 watts. And then if you divide that power out divided by the 0.9, you get 0.7 watts of power in. And then the I out equals 140 milliamps, which is essentially 0.7 watts divided by 5 volts. One of the takeaways from this is that the input current never equals the output current. And so what this buck does really is it's a conversion of the input power to the output power. And the point of departure for a synchronous buck kind of assumes 100% efficiency. So the W in would equal the W out. And of course, if the V out goes down, then the I out has to go up. However, it's never 100%. There's always going to be some losses, as we described in the previous. So 90%. So then you assume that's where step 2 comes in, is you factor in the 90% efficiency. An LDO does a very similar thing. It's a step down, right? It regulates the V out, as does the synchronous buck. I forgot to mention that. It regulates the V out. But it does it in a completely different manner. It takes the V out, again, it's 5 volts in, 3.3 volts out. This is just an example for an LDO. And it takes the output, puts it through an internal attenuator, sends it to the minus input of an error amp, and the plus input is tied to a VREF. That VREF is designed to be very, very stable across process, voltage, and temperature variation. So that VREF is aligned with that 3.3 volt out going through this attenuator. So when these two equal, so this error amplifier will do whatever it can to its output to make sure these two inputs equal. And that's driving the gate drive of this MOSFET. In this case, it's an N channel, but it could be a P channel as well. The idea is you vary the gate drive such that these two will satisfy each other, and you regulate that V out. So it's got an analog control loop, which is quite fast. Meanwhile, you've got this V in versus V out, which is called the dropout voltage, which is V in minus V out, or the VDS. And so if that dropout voltage is low, then the efficiency goes up. If that dropout voltage is high, the efficiency goes down a lot. For example, with 5 volts in, 3.3 volts out, we've got a VDS or a dropout of 1.7 volts. You can expect a 66% efficiency. If you decrease that VDS or that dropout to 500 millivolts, 3 volts in, 2.8 volts out, that efficiency goes up to 84.8%. So one of the big takeaways, though, is the input current equals the output current. Remember, by varying the gate drive of this switch, essentially we're treating this like a variable resistor. And so we'd be following Ohm's law with a variable resistor in a series circuit. This would be basically the same current on the input and the output. Another takeaway, and again, that's dramatically different than the buck, where the input current never equals the output current. It's also a lot more inefficient. And so that inefficiency, which we've described here, creates more power dissipation on the die, and that increases the junction temperature of the die. Okay, so for an LDO current calculation, so if you have a load that needs 100 milliamps at 1.8 volts, and you have an LDO here and an LDO here, and this is 3.2 volts and this is 5 volts, to solve for this I out, because input current equals output current, is pretty straightforward. this is 100 milliamps here. This would be 100 milliamps here. That means this is 100 milliamps. So the DC to DC2 I out, the DC to DC1 I out would be 100 milliamps. Now, if you expanded this and you had 3 branches of power going from the output of LDO DC to DC1, which is an LDO, to DC to DC2, 3, and 4, all requiring 100 milliamps, now this I out will be the sum of these 300 milliamps or 300 milliamps. Now I'm going to pivot to talk a little bit about our data sheets and junction temperature. In all of our data sheets, and that's the same with our competitors, we all have these AC and DC parametric tables. And that's where we guarantee the minimum and maximum parametric performance versus the published conditions. And a lot of times that's driven by the temperature of the die or the ambient temperature. And you can see we typically have maximum operating temperature and minimum operating temperature. And as long as you stay within the min and max, we guarantee the parameters we publish in the data sheet, same with our competitors. If you go outside those, we no longer guarantee the parameters in the data sheet. And then if you go outside the absolute max temp or the absolute min temp, damage may occur to the die or the product, and reliability may be affected. So let's look at a real world example, the NCP 163 LDO by onsemi. And you can see in the back of the tables, this is an excerpt highlighted in yellow, its max junction temperature is 150 degrees C, and the max minus is minus 55. So those are the min and maxes for the absolute. If you look at this is a section of the electrical characteristics tables, the DC tables, which has some output voltage accuracy and line regulation, operating input voltage. You can see the minimum and maximums. Those are guaranteed from 125 degrees C down to minus 40 degrees C. The typicals are what you should see at 25 degrees C temperature for the junction temperature. And so if I were to superimpose these numbers on my graphic, you can see that it's 150 minus 55 for the absolute and between minus 40 and 125 for what we guarantee. Now, not every device is the same. On the left, I've got our NCP 114 LDO. On the right, I have our NCP 189 LDO. Both are good to 150 degrees C maximum temperature. However, on the left, we go to 85 degrees for the 114 for the min and max tables, minus 40 to 85. And on the right, for the 189, we go to minus 40 to 125 degrees C. So I bring this up because later in my Hyperlux image sensor power tree tables, I capture these numbers because you don't want to exceed these numbers. So it's a big deal, and each device is different. Now, for power dissipation for an LDO, the formula is PD, power dissipation, equals Vin times I ground plus I out times the dropout voltage, which is Vin minus V out. Now, this I ground are teeny weeny numbers, typically like I've got a couple of data sheet excerpts for 1.8 volts V out and 3.3 volts V out. And these I ground numbers, these units are microamps. And so it's, less than a milliamp or right around a milliamp. So I tend to ignore this section and just focus on this for power dissipation, because this is really what's going to drive the power dissipation, is the I out times the dropout voltage. And then I want to pivot to talk about theta JA, which is basically the self-heating properties of one of our devices. This particular cross-section drawing I have here is a DFN package, or a dual flat pack package, no lead. And so you've got the die here, it's a cross-section. Here's the mold compound, or basically the encapsulation, the plastic. The die sitting on a die attached paddle, and then the die has these wire bonds that go out to the lead frame. Here, that lead frame makes contact with the outside world in the form of these pads, and we also have a thermal pad in the middle that helps relieve some of the temperature of the die. And these all mate or get soldered to the PCB footprint in copper on the top metal here, and then goes off and it does some interconnect with other devices. And so the whole idea with the theta JA is, this die is going to start heating up as it dissipates more power. And the theta JA is the thermal resistance to ambient temperature from junction. and that's described in degrees C per watt. So if you have a theta JA rating of 65, that means the junction temperature rises 65 degrees above ambient for every watt that's dissipated on the die. So a lower theta JA rating means a lower junction temperature, assuming the same power dissipation. And because the junction temperature is a function of theta JA and power dissipation, the measured theta JA of every IC is published in the data sheets and is often used as a criteria to compare IC products across different semiconductor suppliers, or even within one semiconductor supplier. Now, there's three different types of heat transfer the physics teaches us. One is conduction, which I've captured in the solid red arrow, thermal conduction. The second is convection, which I've captured in this wider arrow with the tails. And then radiation, which is captured in the squiggly arrows. So conduction requires physical contact for the medium. And so in other words, the molecules need to be right up next to each other for that conduction transfer to occur, which happens with the die and the mole compound in this example, and the die attached paddle going down to the PCB below. Convection is more a function of fluid or air as the medium, which you can see happens with the across the packaging with the airflow. And then radiation can occur inside of a vacuum, so no mediums required. And so one of the big takeaways from here is that the theta JA measurement is highly dependent on the PCB design. In fact, according to the JEDEC standards, 60% of the theta JA measurement is dominated by the PCB design. So JEDEC standardized the theta JA measurements with the JES D51-X series of documents, where the -3 defines a single layer 1S PCB design, and the -7 defines a 4-layer PCB design, 2 signal layers, a power plane, and a ground plane called 2S2P. And so this enables a better apples-to-apples theta JA correlation across semiconductor products and suppliers. And there's a couple screenshots of the -7, where you have 4 layers here, the top layer, the bottom layer, and 2 inner layer planes. And of course, that gives you, more mass, and copper conducts heat very well. And then these are some of the layout examples. There's no time to go into that too much here. The point is that there's a standard. Now, it's not perfect. There are some different interpretations of the specifications of -7 and 3 by different suppliers, a little bit of subjectivity, but nonetheless, it's a really good standard. We abide by it, all our suppliers abide by it, and it helps end users be able to, like I say, use an apples-to-apples comparison. Now, I want to point out one former blind spot of mine. I'm just going to use this NCP 163 as an example. It's rated for 250 milliamps. So in the past, before I did this exercise, if I wanted to use that device, I would use it for like a 200 milliamp load, or maybe 225. I'd leave a little headroom because I know it's not super efficient. However, I kind of eyeballed it, and I want to walk through this slide to show that's not a good idea. And I'll start off with the thermal characteristics, which, is 108 degrees C per watt for the wafer level CSP package for this particular device. You'll notice the -7 JEDEC spec that we abided by. And recounting the fact that the die temp is a function of the power dissipation times theta JA, which in this case is 108 degrees C per watt, plus the ambient temperature, where the power dissipation is I out times the dropout, which is this function here. So if I just assume right here, 5 volts in, 1.8 volts out, 250 milliamps, with an ambient temperature 25 degrees C, if I run that through my formula, my die temp's 111 degrees C. My max die temp operating is 125 degrees C. Again, that's not the absolute max temp. That's what the parameters are guaranteed in the tables on the back. So everything's cool, but if I change the ambient to 60 degrees C, which happens all the time, many applications go to 60 degrees C. In fact, all of our image sensors, all the features of our image sensors are guaranteed up to 60 degrees C. They work up to 85, but not every single feature. You'll see the die temp on the LDO is 146, so it's well above 125. So that's not cool. I can't use that. If I drop the I out to 225, it's still above 125. Same thing for 200. It's not until I get to 175 milliamps that I'm below the max temp, but that's less than 5 degrees. So I'm a little more comfortable. I'm a little conservative. So I'm a little more comfortable with 150 degrees. 150 milliamps. Who would have thunk that a 250 milliamp LDO, and I'm not picking on the 163. This is true of all LDOs. Who would have thunk that rated at 250, you really should use it at 150 if the ambient's 60 degrees C. So this is a very, very important exercise that everybody should use for their LDO selection, not only for image sensors, but just LDOs in general. Bucks are a little different for their self-heating. The power dissipation equals power in minus power out, where power out equals V out times I out. Power in equals power out divided by the efficiency. And the efficiency you get from the plots in the data sheet, V in is whatever the application is, as long as it works. And you don't exceed the maximum of the buck. And then I in equals power in watts divided by the V in voltage. And then the die temp formula is the same as LDOs. It's PD times theta JA plus the ambient. So if I pick 5 volts in, 470 milliamps, 3.2 volts output. So the red line is 4.9 volts in, 450 milliamps is right around here. So I'm going to say 90% efficiency. You run the numbers. My die temp is just under 71 degrees C. So if you compare apples to apples, the LDO versus a buck for the same conditions, 5 volts in, V out of 1.8 volts, I out of 350 milliamps, ambient temperature is 60 degrees, LDO versus buck, the die temp, and you'll notice that the theta JAs are pretty similar. It's 60 degrees for the LDO and 65 for the buck in these two cases. The die temp is 170 degrees C for the LDO at a web pricing of 26 cents. Now, web pricing is the low volume pricing, that we put on our website. That's low volume pricing. The equivalent buck is 40 cents at 65 degrees C, and that doesn't include the inductor. So you pay for what you get, right? There's no free lunch. So LDOs are a great option if the 107 degrees C is okay. If the 107 degrees C is not okay, then you want to lean more towards the buck, even though it costs more because that efficiency. And one of those reasons for that consideration is whether or not you're an enclosure or a module. A lot of these image sensors are inside modules or enclosures. So it doesn't have the luxury of having all this free airflow and a large PCB plane underneath it with a bunch of layers to wick away that heat, right? That's nice if you have that, but you may not inside an enclosure or module. Where an enclosure or module is going to trap that ambient air inside the module and can accelerate the self-heating by raising or trapping the ambient temperature inside the enclosure. And now these ICs become more like little Bunsen burners. They're heating up that ambient temperature. So that's a consideration. Also, whether you're grid powered or off-grid powered. So on the left, I've got grid powered, and this is kind of a high level, view that I have. If you have your application has a load and you've got, you're plugged into the wall, somehow, whether it's PO or, an AC to DC adapter, in a sense, you've got an infinite amount of power powering your application. And so, we all want to be good stewards and green, but efficiency, is not a big, like if the LDO will cost a lot less than the buck, you might be better off going off with the LDO because you have an infinite amount of power here. Not the same thing with a battery powered application where you're off grid or energy harvesting or solar. You don't have an infinite amount of energy. So you might be more inclined to use a buck because it's more efficient. You're going to have a longer battery replacement charge interval than if you go with an LDO, which is going to have shorter battery replacement or charge intervals. So these are other considerations as well. And I do preface that this assumes, a 500 millivolt or more step down. So in the past, my rule of thumb for picking an LDO versus a buck was more or less, if the load is less than 200 milliamps, go with an LDO. Above 200 milli, go with a synchronous buck. But, catch me on a different day, that number might be 300 milliamps. A different engineer, that number might be 500 milliamps or 700 milliamps. A better rule of thumb is start with LDOs because they cost less until the calculated die temp is roughly 15 degrees below the headroom, max die temp of the DC tables of the datasheet, not the absolute max die temp. And if you hit that headroom, then you want to pivot to a synchronous buck. That's the best bang for your buck and LDO. Possible exceptions, as we've mentioned, is enclosures or modules, which can accelerate the IC self-heating, raising or trapping the ambient temperature, or lithium-ion powered applications like IoT, where that higher efficiency gives you longer battery life. Okay, now I'm going to pivot to the image sensor power supplies, the Hyperlux image sensor power supplies. There's three major supplies: the VDD-IO, which I have in this column, the VDD, which I have in this column, and the VAA, which I have in this column. And what I'm going to do is slice and dice it with two different criteria for power integrity. There's more than this, but these are the two high-level ones. The first one is the voltage rail tolerance. What's the max minus the min voltage that each supply rail can handle? And the second one is the noise. And so for the voltage rail tolerance, I don't really care too much about the VDD-IO and the VAA, because the VDD-IO can handle plus or minus 100 millivolts, and the VAA can handle plus or minus either 100 or 200. It's this VDDA supply that I have a higher concern for, because it's tighter, right? Its min to max is 50 or 100 or 60 millivolts, depending on the image sensor. And so I want to pick either an LDO or a buck that has very accurate V out plus low and fast transient responses. And I'll talk about that more in the next couple of slides. The other thing is noise. For the first two, the VDD-IO and the VDD supplies, I don't care too much about the noise. Not the case with the VAA supply. The VAA, these image sensors are basically a parking lot of ADD converters at a high level converting photons to electrons. So these ADD converters have, a number of bits, and the maybe 10 bits, 12 bits, 14 bits, depending on the resolution. And the LSBs are going to be chattering with any power supply noise coming into the device. And you don't want that chatter. Those LSBs are chattering, you're going to not have as good, your signal quality, your image quality is going to be reduced. You want a quiet input so you can make use of the full resolution of all your bits. So I want an LDO there with high PSRR. I like to see greater than 85 dB, and also very low noise, less than 10 microvolts. And the layout, I want that LDO very close to the VAA balls or the supply of the image sensor. The closer, the better, because you have less noise with the traces, long traces. And so I'm going to then talk about LDO transient response and V out accuracy. On the right here, I've got a device under test, a load that's got a VDD of 1 volt plus or minus 5%. So this V out needs to stay within plus or minus 5%. Its accuracy is 2%. And so if I graphically represent that, I've got my V in rail of 1 volt plus or minus 5%, which is 50 millivolts. And if I have a transient load here, that will cause the V out to, because of this control loop, that V out's going to take a little time to catch up. And so that V out's going to go down a little bit when the load goes high, and it's going to go up a little bit when the load comes back to 0. And so this response is plus or minus 40 millivolts, and you stay within the plus or minus 50 millivolts, so everything's cool. But you really need to factor in the V out accuracy, right? This assumes a perfect V out, which you shouldn't assume. So if I assume the worst case V out, a plus or minus 20 millivolts, now we could exceed the plus or minus 50 millivolts with the low transient response. So you need both good V out accuracy plus good transient response. And so our new Treo 165 device, the T30 LMP SR 165, which will release in Q4 of 2025, is built on our Treo process, which is it's 1 volt to 90 volts, 65 nanometer, 300 millimeter onshore fab in East Fishkill, New York, and has excellent transient response, excellent dropout performance, 35 millivolts at 0.3 amps, and also very good accuracy. So I want to hone in on some real world example of our transient response. These are actual image sensor load profiles. There's 3 of them: load profile 1, load profile 2, load profile 3. And the x-axis is the I out current, and then the y-axis is time in microseconds. So you can see that these 3 load steps are very close to each other. I call them spiky loads. Load step 1 to 2 is just right around a microsecond from each other. And down below, we've got the transient response, or the V out changes, or transient response, in red of the competitor and in blue with our Treo LDO. And you can see in the Treo LDO, the envelope of transient response is captured in blue, and the envelope in transient response for the competitor is captured in red. And you can see that ideally that image sensor for this VDD, for this specific supply, and I don't even know what supply it is, doesn't really matter. It doesn't want that supply to change at all, but it has changed. And so less change is better, and we're much better than the competition here. But that wasn't the main thing that the customer is interested in. The customer accepts some amount. There's going to be a transient on the V out. What it really cares about is the settling time. How long is what's the time for V out to return to the pre-load step voltage level? And so for load step 1, you can see that in blue, it took us 1.2 microseconds to get back to where we were, where the competitor was 1.8 microseconds, a savings of 0.6 microseconds. That 0.6 microseconds could matter a lot depending on the functionality of the image sensor. It may be chattering, those LSBs may be chattering during this time where they're not chattering here, for example. So we're 33% better than the competition. For load step 2, we're 44% faster and better. And load step 3, we're 42% faster. So real significant Treo advantage over the competition for the low transient response. Faster and less is better. Also, the dropout voltage, I think we spec 35 millivolts for the dropout. However, we operated 35 millivolts dropout, but parameters like PSRR and noise and other parameters, we need a 100 millivolt minimum dropout. So if you consider a 100 millivolt dropout, in other words, for example, 2.9 volts in, 2.85 volts out, so 100 millivolts difference, V in, V out, with a 300 milliamp load, our efficiency for this LDO is 96.6%, because we have super low dropout. Most of your LDOs spec a minimum dropout. I don't know, you have to look at the data sheets, but something like 300 millivolts, 250, 275, 200. We go down to 35, guarantee PSRR and noise at 100 millivolts. So your die temp is only 63 degrees C. So I just wanted to point that out. And then power supply rejection ratio, that's the ability, the LDO, to be able to attenuate input ripple on its output. So let's say if you have input ripple, especially like, bucks are known for generating ripple, as we mentioned. So a high dB number means it attenuates more of the ripple on its output. And that's what you want. Like that VAA supply on the image sensors, you don't want a lot of ripple on that. You want as minimal amount of ripple as you can. And that's why I like the NCP 163, because it offers 92 dB PSRR at 1 kilohertz, as well as 6.5 microvolts of RMS noise. And here's 2 plots of the PSRR for the 163 with 1.8 volts out and 3.3 volts out, with different loads, color-coded for different loads across the frequency. And again, really good bang for your buck, 11 cents for one of the best, that's web pricing, or budgetary pricing, low volume pricing, but one of the best LDOs out there for PSRR. Now, this is a high-level summary of bucks versus LDO, assuming a 500 millivolt step down. And you can see the LDO in green has it all over the synchronous buck for inductor, EMI, cost, noise, PSR, and PCB space. The efficiency, the synchronous buck has it all over the LDO, as well as, higher loads, bigger loads. The buck is the way to go. And then IQ, you can find the quiescent current, you can find, low to medium IQs for both. And these are a couple of examples of bucks that I'll be using for their power tree further on. The 53730, which is a 3 amp buck, 2.3 volts VN to 5.5, and then the 745, which is a 1 amp buck. Excuse me. And then also our PMIC, our 92310. What's really nice about this, it's a power of a coax PMIC. Power of a coax is a certain cable used in the automotive world. What that means is it accepts an input of 5 volts to 18 volts, and that comes into this DC to DC1. In a DC to DC1 bucks that down by default to 3.3 volts, and then that drives these 3 DC to DCs. The first 2 are bucks, and the last one's an LDO. This LDO typically drives a VAA supply. These are the default voltages. The DC to DC3 typically drives a VDDIO, and DC to DC2 typically drives a VDD supply. And you can vary across I2C the outputs of all 3 of these devices. And then the AB trim option is in mass production. The AD trim option is coming, and these are the default outputs. And all these VOUTs are I2C programmable after power. Okay, so now we'll transition to the 11 image sensors that I'll be covering today. The part number, the family, the number of pixels, the shutter type, whether it's global shutter or electronic rolling shutter, the backside lamination, the ITOF, which is indirect time of flight, which is, we have the AF0130 device. And that's a really cool device. It works in conjunction with the laser, where it controls a laser and sends out a laser pulse, and then it measures the phase coming back. That's why it's called indirect time of flight. Doesn't actually measure the time. It measures the phase coming back and can measure distance and depth, the depth of an image. Super cool part. Then wake on motion, and then also a power supply turn on and turn off sequencing. This whole presentation, I'm not going to go into the image sensors very much themselves. It's all about the power tree. And then I expanded that to capture, so here are the 11 image sensors, the families, the number of pixels, and then these 3 columns are VDDIO, min, tip, and max voltages. These 3 columns in light red are the VDD supplies, min, tip, and max. And then in green, I've got min, tip, and max for the VAA supplies. And then in white here, I've got the typical currents for each supply for VDIO, VDD, and IAA. And most importantly, in yellow, these are the maximum currents, assuming 60 degrees C, ambient temperature, and the image sensor is configured for highest power consumption, meaning I've got all the knobs turned on for the features and the high res. And so these are the currents. And these currents are what I used for the power tree. Excuse me. My individual power trees assume basically worst case currents. Okay, so let's jump into each tree. So the first image sensor is the ARX 383. It's part of the SG family. Here's 5 volts in. And so I've got a block diagram. Here's the ARX 383 here with the 3 supplies. In the circles capture the power up sequencing. The squares capture the power down sequencing. These numbers are the max voltages and currents. I should say the typical voltages plus or minus the tolerance and the max currents. And then I'm using the NCP 163 as DC to DC1. That's going to drive the VAA supply, as well as an intermediate rail at 2.8 volts for the 114 and the Treo device to deliver those loads. This table on the right is basically capturing the total BOM costs, and this is what I call web pricing. This is the pricing we put on our website. So low volume pricing. If you go higher volume, the pricing goes down. And then this table in the bottom captures more details about the devices I've selected. So DC to DC1 is a 163, which is here. 114 is here. And the Treo 165 device is here. All 3 LDOs. This column captures on the left the max die temp in the AC and DC tables, which is important, right? You don't want to exceed these because then your parameters aren't guaranteed. And this column in red is the calculated die temp, however it's sitting in this table. And so this is valuable information because now you know how far you are away from these maxes. Then I had the V in, the I out, the V out accuracy, transient response, theta JA, PSRR, noise, package, and the web pricing. So this is the template that I use for all the image sensors. This is just 5 volts. The next slide is 18 volts and 48 volts. When I go to the next slide, I'm going to replace DC to DC1 with the 737. That 737 is a new wide input LDO, goes from 3 to 65 volts, very cool device. So it's nice to use for this 18 volts in, right? And that's the pricing, because that costs 33 cents. So I changed the pricing for the total of these 3 devices. I also have an alternative for 18 volts in, because this dye temp is 105.2 degrees C. It's still under 125. So that may be fine if you have plenty of airflow. If you're in enclosure, that might be a little warm. So you may want to opt to go with the PMIC, which I have here. And that total dye temp is only 61.8 degrees C. So this gives you some information to make that decision on whether or not, your application is really sensitive to self-heating. And there's the appropriate cost. And then 48 volts, I replaced DC to DC1 with the fan 65,000 family here, which takes an input of 4.5 to 65 volts and a total current of 60 amps. Now for image sensor number 2, I've got the 145. And so you can see the loads are relatively light. So I can use the Treo LDO for the VDD rail, because it's got really good transient response and V out accuracy. I'm using the 163 for the VAA supply because it's got excellent PSRR and noise. And then the 161 is gonna step down to 3.2 volts as an intermediate rail. And here's the dye temp at 95 degrees C. So that might be a little warm. So alternatively, you could, for a little more cost, you can go with a 745 buck, and that dye temp would be 66.7 degrees C versus 95.6. And then 18 volts and 48 volts. And then for the number 3, I've got the 235, similar story, 161, 114, Treo, 163 with the dye temps and the options. And then for the 4th device, the 2020, this load goes up for the VDD to 350, as does the total load. So I'm going to transition to the 189 here for DC to DC1 and DC to DC3. The 189 LDO costs a little more, but its theta JA is 60 degrees C per watt, so its self-heating is lower, which I like. And so I replaced that. I replaced that here and here. However, you could replace DC1 and 3 with a buck if the self-heating above 100 degrees C is a concern. Number 5 is the 830. And that total load is a little less. So I go back to the 161 here, the 114 Treo 163. Number 6, 161, 114, the Treo and the 163. The 822, a little more current. So I'm back to the 189 here, the 189 here with alternatives for the bucks because of the dye temps. Again, the bucks, I've got the 745 or the 730, the 745 here, and the 730 here, 1 amp and 3 amp. And now image sensor number 8, I return to the 161, 114, Treo, 163. And number 9 is the ITOF, Hyperlux. And so that's got a lot more power requirements for the VDD-IO, 3.1 amps. And so now I'm going to use the 3135 5 amp buck that I've captured in the middle row. That's coming right off the 5 volt input. And then I've got the 163 powering the VAA and the Treo device here. That's for 5 volts, 18 volts and 48 volts. Here, I'm going with the fan 65,000, as you can see here, and these 3 devices for the rails. And then device number 10 is the 341, which is a fair amount of power for the VDD supply, and also this stage here for the 3.2 volt intermediate rail. And so that's got a 1 amp buck, the 745, with the 189 LDO here, with the 114 and the 163. And then for the final device, the 823, I'm going to stick with that 1 amp buck here because of the load. And then similarly, the 189 LDO here, but the 114 and the 163. I like that 114. I keep using it because it's a great bang for your buck. I use it almost every block diagram because it's only 5.6 cents. So like I said, that rule of thumb, always go with the less expensive LDO if you can use it, right? You want to save, you want to be wise with your money. You want to be thrifty. And then, so this slide here talks about the pixel data transport. So once that Hyperlux, has its data, it outputs that data on a MIPI parallel bus. And that can go directly into one of our image sensors. I have the AP1302 here with the appropriate DC to DC here, the 730 buck and the NCP114 LDO. That's for local image sensor processing. However, sometimes you'll use remote image sensor processing where you go across a coax cable to a remote processor. And if that's the case, then you'll have a serializer locally. And then the other side of a cable, you have a deserializer or a SerDes solution. And so what's nice about this NCV 92310 PMIC is it was designed to support most of our Hyperlux, as well as, I say most of our Hyperlux, it supports all of our Hyperlux except for the ITOF. It supports all the DC to DC power for the Hyperlux and the serializer, which is very cool. So I really like this device. And so that's how you would do a remote ISP power tree. And so really that completes the webinar today. I really appreciate you taking the time out. I'm happy to take any questions or considerations you might have. And thank you very much for taking the time to listen to me. And I hope you all have a wonderful, wonderful day.